Hello everyone, I am Dr. Nitin Kumar Saxena. In my previous video, I have discussed with you the value of capacitor, capacitance, how can we define them, and we have given you the derivation for the value of capacitance in case of parallel plate capacitor. Now in this video, we will see what would be the effect if we are introducing a dielectric material between the two surface of the capacitor A and B. I told you in my previous video that if we have, suppose, a parallel plate capacitor or any type of capacitor having the two surface 1 and 2, and this has, okay, this not look like a equal area. This is wrong. Okay, wrong drawing by me. If you like correctly, if I make, then these two surfaces are equal in area, right? So this is surface 1, surface 2. Here the surface charge density is minus sigma. Here the surface charge density sigma. The area of this plate is A. Obviously the area of this plate is also A. Both are same. And the separation between these two is D. Right? So in starting, I assume that air is filled between air is filled between A and between surface 1 and 2, right? And we know the dielectric strength concept that I have given you in previous video. That what is dielectric strength? Dielectric strength means the capacity of any material to remain unionized when we are increasing the value of potential. Suppose I am saying this is some material and we are applying some potential on it. So when we are increasing this value of V, when we are increasing this value of B, at the value of V up to which this will not ionized is known as dielectric strength. Okay, after this point it will ionized, right? So now I want to increase. We have seen that for air we can increase the potential up to this value. We have seen this. Okay, so we can increase the value of potential up to the value of 3 into 10 to the power 6 volt per meter or 3 into 10 to the power 4 volt per centimeter in case of air. Now if I want to increase the value of potential between the plates, what can I do? I can use the different dielectric materials. And I know the property of dielectric material that I have already discussed in my previous video, that if we have any dielectric material, so dielectric material may be of two types, polar type or non-polar type. In both the materials, if we are providing any electric field, so what will happen? Due to this electric field, all the positive and negative charge particles will be at these surfaces, and they will be in opposite direction. Okay, how they will be in opposite direction? How they will be in opposite direction? The opposite direction means if electric field is moving, electric field lines are from this surface 1 to surface 2. So the negative charge will come across this surface and positive charge will come across this surface in dielectric material. That all we have discussed in detail in my previous video. You can refer my previous videos for getting the good understanding about the behavior and mechanism in dielectric material. Right. So to understand the concept here, like if we have a dielectric material, dielectric material between parallel plate capacitor. So to understand this concept, what we are assuming? We are assuming the same and fitted dielectric material between these two plates. Suppose I am saying these are the plates. So the same, like from this surface to this surface, our dielectric material is equal to the exactly equal to the volume between these two plates. Okay, this is the plate. So exactly it will be filled between these two plates. And if I am saying if I am saying that dielectric material has the surface charge density, dielectric material has a surface charge density, say del P. Okay, so what will happen if I am putting this sigma P, this dielectric material exactly between these two plates? What I am assuming that the size of this dielectric material is equal to the volume between surface or parallel plate. Surface is what? Parallel plate 1 and 2. Okay, so if it is exactly placed in it, so what will happen? You see, we have plus sigma here, and exactly this sigma P is inserted in it. So what will happen? At this side, at the side of the A, at the side of A, okay, what will happen? At the side of A, we have this sigma, this is minus sigma. This minus sigma P will appear due to this surface, and plus sigma P due to this surface. What will happen in this case? What will happen in this case? Exactly we will get the surface charge density at surface 1 equals to sigma minus sigma P. Similarly, at surface 2 minus of sigma minus sigma P. Right? This is clear because this we have value sigma and this is minus sigma because of this dielectric. So what will happen? The resultant surface charge density at the surface will be sigma minus sigma P, and here minus of sigma minus sigma P. Right? So if we have this surface charge density, so this means the electric field is given by sigma minus sigma P upon epsilon naught between any point of this parallel plate. Right. Then what is the value of V? V is given by again sigma minus sigma P upon epsilon naught into D. Right? You see here the net value of sigma, net sigma is reducing. You see here net sigma is sigma minus sigma P. This means the overall surface charge density is going to be reduced after inserting dielectric between plate 1 and plate 2. So In place of writing sigma minus sigma p, I can write sigma upon k, where k is any number which is more than 1. Right. So if I put, suppose k, I put 2. So what will happen? This will be sigma upon 2, means zero point 0.5 sigma. So ultimately this whole value is less than the value of previous sigma. Is it fine? So in place of writing sigma minus sigma p, I can write sigma upon k. What is k? K is any constant which value is more than 1. So if I substitute here, what I will get? I will get sigma d upon k epsilon naught. Right? And what is sigma? Again, sigma is q upon a. If I am saying the total charge is q, so q upon a. So q upon epsilon naught a d into k. Okay, k epsilon naught q upon a into d. This is clear? So what does it mean? This means you can say here that this k epsilon naught can be defined by new variable. Epsilon is k epsilon naught, right? So this we have studied. The epsilon naught is the value when we are working in vacuum, and if we are moving to any medium, then we have multiplied with this constant k, and k is defined as permittivity of material. Okay, so k is defined as permittivity of material. And you see here again, if I'm again putting it like, what is the value of c? Cq is given by cv. So if you see this formula, so again you will say c is epsilon a upon d, where what is epsilon? Epsilon is k times epsilon naught. So this will be the formula for any dielectric material placed in the parallel plate capacitor. And you see the value of k is 1 for vacuum, and in general k will be more than 1, right? And hence if I compare, finally if I compare that, okay, sorry, the value of c is given by epsilon naught a upon d, and c is given by k epsilon a upon d. This is in vacuum, means the parallel plate capacitors, between parallel plate capacitor there is nothing. And if we have any medium, dielectric medium, maybe air, maybe anything, so we put it here k. So this in general, so if I am saying this value vacuum will denote by epsilon naught, if I divide both the equations, so what I will get, c naught upon c is given by epsilon naught k epsilon naught, again this is cancelled, so c is given by k c naught. So c naught is the capacitance when we have vacuum in the plates 1 and 2, and in general it is, if we want fill a material with permittivity k, the new value of capacitance will be c, and hence we can increase the value of capacitance by inserting any dielectric material between the plates of the capacitor. So finally we can conclude, if we want to increase the value of capacitance, so we will insert a dielectric material between the plates of the capacitor. So I hope the concept of dielectric material between parallel plate is clear to you. So this gives the explanation how we can increase the value of capacitance by simply inserting the dielectric material between the plates of capacitor. Okay, so I hope this concept is clear to you. Now let us move on the combination of capacitors. If we have, like, if I am saying if we have more than one capacitor, then what will be the value of their combinations? So to see this, suppose I have two capacitors which are connected with this battery B, right? This is capacitor C1 and C2. The two capacitors are connected in series with this battery B, and I want to make an equivalent circuit in which a single capacitor C net, or I can say C equivalent, is connected with this battery B. Right? So in place of the combination of two capacitors, I am putting an equivalent capacitance. So my question is that what will be the relation between the C equivalent and C1 and C2? So let us start with the basic concepts. Then if we are connecting these two capacitors in series with this voltage source V, so what will happen? A charge will start flow from this voltage source and it will go to the plate, right? How it will move? It will move in a way that same charge will go on the both capacitors, right? So if I am saying here the plus Q charge, then here will be minus Q charge. Here, from here, the plus Q charge will move in this direction, minus Q charge will move in this direction, right? If this plate has minus Q charge, so an equal and opposite charge will appear on this plate, plus Q. And similarly, if this has plus Q charge, this has minus Q charge. And you see, this plus Q minus Q will cancel out with each other, and the charge on this plate is plus Q, the charge on this plate is minus Q. So in general, we can say if we have capacitors connected in series, the same charge will be on each capacitor. Okay, so in series, we can conclude that in series, same charge will appear on each capacitor. This is fine. So same charge will appear on each capacitor, right? Again, you see here this V, when we are giving the potential, this potential is given to C1 and C2. So this will be like this. Okay, so this means here the capacitance C1, charge is Q here. So the total potential V, which is going on these two capacitors C1 and C2, will distribute like this. So second point, we can say in series, total potential will be divided on each capacitor Okay, in series, total potential will be divided on each capacitor in such a way, the sum of potentials on each capacitor will be equal to the supply pole potential. Okay, in such a way that potential on each capacitor, if we sum, then it will be equal to the total supply potential, right? So these 2 points are clear. So if I like write mathematically, so what I will write, V will be V1 plus V2. V will be V1 plus V2. V1 is the potential at C1, V2 is the potential at C2, and V is the total potential given by the supply. So same thing here, you can say if this is V, so this will give plus Q and minus Q over here. So if I write here the V, in place of this we are writing this. So what I can write? I can write, because both the figures are equivalent, so I can write this as Q upon C equivalent from this figure, and from this figure V1 is given by Q upon C1 and V2 is given by Q upon C2. So what I will get? I will get, okay, so this is the formula if two capacitors are connected in series. In general, if we have number of capacitors connected in series, then the formula is given by for n number of capacitors connected in series, C1, C2, C3, C4 up to the Cn. So this will be the general formula. In this way we can get the overall capacitance value for the combination of capacitors connected in series, right? In the same way, if the capacitors are connected in parallels, then what will be the equivalent capacitance? How can we find? So again, if we have number of capacitors connected in parallel, so let us start with two capacitors C1, C2 connected with this voltage source V, C1, C2, and this is equivalent to a structure where we have the equivalent capacitance C, which is connected with this voltage source V. Now you see here what will happen. In this case, C1 and C2 both are connected in parallel. So when we give supply V, so plus Q charge will move from this plate of both supply. It will go like this and it will appear. When it will go from this point, the charge, what will happen to the charge? Some charge will go to this point, this plate. Some charge will go to this plate. Okay, so let here we have the charge Q1, here we have charge Q2. Since it is going from positive plate, so it is plus Q, this is plus Q2, and from negative plate, here the charge will be minus Q1, here the charge will be minus Q2, right? And you see these 2 points are same as these 2 points, similarly to these point. So if I am saying the potential across these 2 points is V, similarly the potential across these 2 points will be B, and similarly the potential across these 2 points will be V. So what does it mean? It means, number one, potential across each capacitor connected in parallel with supply V will be same and equal to supply. So what is the first point? If the two capacitors C1 and C2 are connected in parallel with the supply, so the supply potential will appear here and here. So the potential V will be across C1 and across C2. Second point, if plus Q charge is moving from this plate, so it will distribute among the capacitor C1 and C2. The charge on each capacitor will be each capacitor will be divided from the charge supplied from supply in such a way that total charge will remain conserved. Okay, so the charge on each capacitor will be divided from the charge from the supply. So supply plus Q is going from the supply. It will divide on C1 and C2 in such a way that total charge will remain conserved. What does this mean? This means the total charge is Q. So this is divided as Q1 and Q2. So this means Q is Q1 plus Q2. The same thing we can say in this figure also. Yes, plus Q is going here because for this C1 and C2 the equivalent structure is given by C. So in place of writing two capacitance C1 C2 in parallel, we are writing a single capacitance which is given by C equivalent, right? So Q is Q1 into plus Q2. If I write the value of Q from this equation, what I will get? I will get C equivalent V, right? What is the value of Q1 here? C1B, because this potential will come across this and here also plus C2V. So we will get C equivalent is C1 plus C2, right? So if we have two capacitors in parallel, then equivalent capacitance can be given by adding the capacitance of each capacitor. If we have more capacitors connected in parallel, then general formula will be, right? So this is the most general formula. So to understand this more, I am giving you a very simple example. Suppose a very simple example. Suppose okay, so this is a simple structure in which we have three capacitors connected in this arrangement. So what would be the final equivalent C between A and B? This is our question. So you see this figure, you have three capacitors. Two capacitors are in series first, and then this is in parallel with this. Okay, let me allow to write this for the sake of the simplicity of the calculation. I am writing it 20 and this is also 20. Okay, just only for the simplicity of calculations. If you take 5, 5, then answer will also come. Okay. So, okay, we will do with 5, 5, otherwise you will confuse. So, I am writing this 5 microfarad, 5 microfarad, and both are in series, and this is connected with 10 microfarad, which is in parallel. So, if I want to calculate, so first I'll start from this point. This both capacitors are in series. So I can replace the two capacitance by a single capacitor. So if I'll replace it, the new structure will be like this. Okay, so these two structures are equivalent. This is 10 microfarad. And for this 5 microfarad, I am writing suppose C. Suppose C1. So what is C1? C1 is when 5 and 5 are in series. So 5 and 5 are in series. So their combination is given by C1. So what will be the value of C1? This we have the formula. 1 upon C equivalent is given by 1 upon first capacitor plus 1 upon second capacitor. When we will solve it, what we will get? When you will solve this, you will get 2 upon 5. So 1 upon 2.5. So C1 will be 2.5. So what is the value of this C1? This C1 is 2.5 microfarad. Right? Now you see, this C1, which is 2.5 microfarad, and this 10 microfarad are again in parallel. So in place of this, what I can do? I can replace another capacitor, C2, right? So what is 2.5 and 10 are in parallel. So if they are parallel, so what is the formula for parallel? Formula is C equivalent is C1 plus C2. C equivalent is given by C2. Okay, we are denoting the equivalent values denoting by the C2. So C2 is 2.5 plus 10, 12.5. So what is this? 12.5. And you see, this is the value between the value A and this is between A and B. So what is the answer? So in this way, we can find the overall capacitance between A and B. So what we did, I am again repeating, 5 and 5 first, they were in series. So I used the formula of series, 1 upon C equivalent is 1 upon C1 plus 1 upon C2. I solved, I find the equivalent capacitance first. Then this and this both are in parallel. So then both are parallel, so I put the formula for parallel, C equivalent is C1 plus C2, and finally this is our answer. So I hope the concept of combination of capacitors in series and parallel is clear to you. So let me allow to finish this lecture at this point. Thank you very much.